Hi. Sometime back I did a titration of oxalic acid with sodium hydroxide. Let's just have a look at part of that video. So let's switch on our scale, but before we do that, let's put a piece of paper on it and switch it on. It's going to zero itself, and you'll see it comes to zero with a piece of filter paper on it. There it says zero. So we're going to take some oxalic acid. You'll see that it looks like sugar. We're going to make sure that it's crushed. We don't want chunks of it. We want approximately, let's get a teaspoon of it. How about that? There's a teaspoon. It looks, and we put it carefully on our scale. And it says 6,34 grams. Okay, let's take that. 6,34 grams. We can carefully pick up every little grain of this. And now we're going to throw it into this flat-bottomed flask. Let me put this here. So, making sure we don't lose any of it, I throw it into the flat bottom flask, shake it all in. Now, it would be nice if we had one of these flat bottom flasks with a thin stem and you could just fill it up to a certain amount, but instead I'm going to have to use a measuring cylinder, and I'm going to throw in, well, this measures up to 250 moles. So I'm going to throw in just less than 250 moles. And we hope that it will all dissolve. Okay, that looks like it's more or less dissolved. So when that's completely dissolved now, we're going to take our measuring cylinder again, as I say, because we don't have one of these that has got a nice thin stem. We're going to pour it back in here. So we've left nothing behind, and then I'm just going to fill it to the 250 ml level with a wash bottle. So here is what we're aiming for. And we're going to make sure that the bottom of the meniscus is touching. Today we're going to continue with grade 11 stoichiometry, which means the ratios between reactants and products. So if we go and look on our CAP syllabus, it says calculate molar concentrations of a solution, perform stoichiometric calculations using balanced equations that may include limiting reactions. Okay, so 58 and 59 we want to have a look at today. So let's go to our BFF, or best physics friend. No, it's not the periodic table, it's this. It is our data sheet. There it is for paper 2, chemistry. And it's got a few constants there. Avogadro's constant, remember? A mole is if you take 6 and 23 noughts after it and you count out that number of atoms or molecules, you've got 1 mole. It's a big number, 23 noughts after that 6. So that we learned was a mole. So if we count that number of atoms, we get a mole. So that little n stands for number of moles. If we count double the number of atoms, 2 times that, we're going to get 2 times n, or 2 moles of it. Now, here is a formula. Number of moles is number of particles over Avogadro's number. So if we've got twice Avogadro's number divided by Avogadro's number, we're going to get 2 moles. Now have a look at this formula here. Number of moles is mass over molar mass. Now you remember we said that if you go to your periodic table and you look at this number here at the bottom, 4, 1, 7, 9, etc. Say, let's take it for oxygen as 16. If you have 16 grams, that mass number, in grams, you've got exactly 1 mole. So how much would a mole of fluorine have a mass of? 19 grams. How much would a mass of hydrogen have? 1 gram. How much would carbon be? 12 grams. So if you have exactly that number in grams, you've got exactly 1 mole. So let's go back to this formula. If we take our mass, suppose we know the mass of carbon is 12 and we've got 24 grams of it. So we put the 24 upon the 12, and that means we've got 2 moles of carbon. And if we add 32 on top, and this mass was oxygen 16, 32 divided by 2 would be 16. So here we can find out how many moles we got by taking the mass of the substance over the molar mass. And then another concept we need to know is concentration. That is the number of moles in a volume. And volume is normally measured in decimeters cubed. That's about a liter. It's a square, what we commonly know as a liter, like a liter of milk. So if we now know the number of moles, we divide it by the volume, we get the concentration. Think of it in terms of a cup of tea. You have 1 teaspoon of sugar in 1 cup of tea. There's the amount of your solute, there's your solvent amount, and then you get the concentration. But another way, if we combine those two formula, is concentration is mass over molar mass, that's number of moles, mass over molar mass, so that would be number of moles divided by volume. And so we can combine those two formulas and just make one formula here. So with that in mind, let's go to a particular reaction which I've got for you. Just have a look at it. This strange compound here is oxalic acid. Now, oxalic acid you can find in spinach. It sets your teeth, that Swiss chard, it sets your teeth on sort of edge. And you also find it in 3-leaf clover. It's got that bitter taste, that sour taste. It's a sour, it's an acid. Now, what makes oxalic acid quite interesting is all acids are proton or hydrogen donors. So here you see the hydrogen, and here you see the hydrogen. So what is interesting about oxalic acid is you see these O's. There's 1, 2, 3, 4 O's, and they all, there's the 4 O's in the formula, they all pull the electrons away towards themselves because they're more electronegative, leaving those hydrogens free to pop off. When they pop off, they form the oxalate ion. So here we see the formula for oxalic acid. But now notice this curious thing. It's got a full stop, 2H2O aqueous. So what this means is called the water of crystallization. You all know that sugar doesn't come from a packet from a shop. You all know it comes in sugar cane. So imagine you took your Swiss chard, you ground it up, and you got your oxalic acid, and you boiled it away till you were left with just this oxalic acid powder. It looks like sugar actually. But within the oxalic acid is captured in, when it crystallizes into a powder, it captures 2 waters with every oxalic acid. So we have to take into account the mass of that water when we take into account the molar mass of oxalic acid. So if we were to work out the molar mass of oxalic acid, how would we do it? Well, look at all those substances that are in it. And let's start to count by looking at our periodic table. There's our periodic table. Let's just get our periodic table. It's got hydrogen, oxygen, carbon in it. So hydrogen's 1, 12, and 16. Those are the numbers that we are going to have to use. Right, so 2 hydrogens is 2 times 1. Then we've got plus, we've got there 2 carbons, plus 2 times 12, plus, not equals, plus 4 oxygens, 4 times, remember oxygen was 16, plus our 2 water of crystallization plus 2 times, well, let's work it all out together, H2O, 2 times 1 for the 2 hydrogens, plus oxygen is 16. So what does that all come to? Well, let's get our calculator. Okay, there's a calculator for us. So we got 2, that's the 2 times 1, plus 2 12s are 24, plus 4 times 16s, plus 4 times 16, plus 2 times, this is 16 plus 2 is 18, plus 2 times 18 equals 126. So we know that the molar mass of oxalic acid with its water of crystallization is going to be equal to 126. And if we express it in grams, we've got exactly 1 mole of our 126. We've got 1 mole of oxalic acid with its water of crystallization. But now let's suppose if 1 mole is 126, how much is 634 grams? Because when I did my titration, I just took 634 grams. So what I could possibly do is I could just use pure logic. I could say this: if 1 mole equals 126 grams, then 6 Now let's go to our BFF and let's go and get a formula to find out how many moles we've got if we've got a mass over molar mass equals number of moles. And let's work out from that how much 6,34 grams of oxalic acid would be worth. So if we got 6.34 grams, we could say number of moles equals mass divided by molar mass. So we're going to find out mass, which is, we got here 6.34, 6,34 divided by 126 equals, let's get our calculator again, um, 6.34 divided by 126 equals, let's write it down, let's look at it again, 0.0503, 0.0503. moles. So that's how much 6.3 grams represents. Now let's go back to our BFF and find out what the concentration is if we put this amount into 100 into 25 centimeters cubed. Now let's look at our formula. Here's a formula. Concentration is number of moles over volume. So let's just work out what the concentration of this is. Once we've worked out the number of moles as being 0.05 moles, we're now going to find the concentration. Concentration is number of moles over volume. So there is the concentration over the volume. We're going to dilute it in a quarter of a decimeter or 250 milliliters of water. That gives us a concentration of 0.2012 moles per decimeter cubed. Now, if we want to find out the number of hydrogen ions, we must double it, because this is a diprotic acid, meaning there's each mole of oxalic acid produces twice as many hydrogen ions, so that times 2 gives us 0.4025 moles per decimeter cubed of hydrogen plus ions. So there we have finally worked out what the concentration was of our solution of oxalic acid if we mixed 6.3 grams or 1 teaspoon in a quarter of a liter of water.